Hello, everyone. My name is Tomek Sterna, and I am leading the project for the new 8-bit x65 computer. But that is not what today is about. As part of this project, a new sound chip called SD1 was created as a sub-project, which I will tell you about today. How did this happen? What motivated us? What are its capabilities?
So this was only supposed to be a side quest.
Because while we were building the new 8-bit microcomputer, we wanted it to have the capabilities of computers from that era. So we have an 8-bit microprocessor. We have a graphics chip that is quite similar to those in the Commodore 64 or 8-bit Atari. And we wanted a sound chip that played like those from that era to have some cool sounds. I spent a long time looking for a chip, preferably an FM synthesis type like OPL or PM that I could use. And it turned out that I managed to find such a chip because until quite recently, up to the year 2020, Yamaha was still producing these OPL line chips.
They were called SD1?
The first prototype of my computer used these chips and they actually sound quite nice. But it turned out that Yamaha has completely withdrawn from producing these synthesizers. They are not making them anymore. There are some leftovers on the market, but they are hard to find. Prices are rising more and more, so I had to make a dramatic decision, and we decided to make such a chip ourselves so that not rely on chips scavenged from old sound cards or hunted down in some dusty old warehouses. So the idea came up to try and make something like that ourselves. Since the SD1 is a synthesizer from the OPL line, Yamaha used only synthesizers that employed so-called additive synthesis, where by layering many sine waves, we could generate a sound waveform. And a large part of my computer's community wanted to go in this direction. The second group are the fans of the SID, the one that was in the Commodore 64. They were super fascinated by the capabilities of the SID. The fact that it is currently still one of the most popular sound chips, and we were wondering which way to go. So I thought to myself, why not both? So we took a bit of both, a bit from OPL, mainly from what ESM came up with. ESS was a company. They made an OPL 3 clone. It was called SFM. It had quite unique capabilities, a bit of SID, a bit of what was in the Atari Poké. It had a very distinctive sound. We wanted to recreate that as well. And also to have samples. These are capabilities similar to what was in the Amiga. We threw it all in, mixed it up, and we have a hybrid chip that simultaneously has the capabilities of an additive and subtractive synthesizer. The chip is designed so that additive synthesis, combining multiple sine waves, gives us the first phase of sound generation, where we have a bass generated. And then the second stage is filtering, just like the SID had. So we have filters, so frequency modulation synthesis builds the timbre, and then we have a block of filters that sculpt it. Personally, I wanted this chip to be able to sound like many old synthesizers, so that chiptunes written for OPL, OPM, SID, and POKI could be played. So it should have those kinds of capabilities so that by setting the parameters accordingly, they could be played. So I wasn't trying to recreate the sound of any specific chip at all, meaning it doesn't have to work exactly like an OPL 3 or sound exactly like a SID. It was meant to have capabilities similar to chips from that era, but it didn't have to be a 100% recreation. And each such synthesizer channel acts like a small synthesizer. We have those operators that generate sounds for us. Then we have a filter and some more hardware-like sweeps, where we can simply tell the synthesizer to change the frequency at a certain speed or shift the volume. The system is stereo, can play samples, and we managed to fit 9 channels. So the characteristics of this first additive module are: the architecture is inspired by what is in the ESFM, where we have 4 operators, but we do not have rigid algorithms like it was in OPM. Instead, each operator can be a modulator for the next or can be a sound generator, and we can freely set the percentage by which the previous operator modulates the next and how much of its output goes to the main output. Plus, each operator is controlled by the main frequency set on the channel. So we set the frequency that the channel is to play, and each operator takes that frequency and can multiply or divide it to generate the harmonic frequencies needed to create a specific timbre. But besides these fixed multipliers, where we can multiply the base frequency by 2, by 4, and so on, each operator also has the option of fine detuning, a slight shift of the generated frequency, and this causes, as time passes, some dirtiness to start being generated. Each operator also has standard envelopes that we know as ADSR, which is attack, decay, sustain, release. But here there is also the issue that besides the 4 parameters, meaning the time of attack, decay, sustain, and release, we also have the option to set a level for the sustain stage. It can also decay. This is needed for and for percussion instruments like a cymbal. When we hit it, even if we keep holding the note, the sound of the cymbal slowly fades away anyway, and we can also simply release the key on such a sound. It is as if we grabbed the cymbal and muted it. Well, there are many, many possibilities. It is also the case that every operator can have the option to set a fixed frequency. It does not take it from the channel then, but it is entered permanently. This is, for example, so that we can add a constant bass or noise to a generated sound. And just as classic Yamaha synthesizers could generate sound using only sine wave operators, the SGU, following the said model, also features square, sawtooth, triangle, noise, and periodic noise waves. And those asterisks, I will come back to them. And the other half of each channel is a subtractive module. It is fed by the sound coming out of the frequency modulation synthesizer. And here we have the filters. They are digitally implemented, but they work just like those old analog filters in the SEED, because the SEED is very well researched. Therefore, I took ready-made solutions here, just as they are used in SEED emulators. So on such a filter, we have the option to set the cutoff, meaning the cutoff frequency where this filter operates. We have the resonance level of a given filter. This is how strongly the filter acts, and the option to enable one of 3 modes on each filter, either a low pass, high pass, or band pass filter. And they, just like in SEED, can be combined. We can turn on 1, 2, or all of them at once, and that also has an effect. All these modules are affected by the filter cutoff parameter. And I mentioned that a characteristic feature taken from the base module this synthesizer was built from is that we can set a sweep. This means we can hardware set the frequency on a given channel to change from one frequency to another at a certain rate. So we can hardware set the channel to perform and it can optionally ping pong between these frequencies or loop. Such sweeps are available for frequency, meaning the pitch for volume and for the filter cutoff parameters. And there must also be PCM. I debated for a long time whether or not to add sample playback to this system, because after all, 8-bit computers from that era usually could not play samples. But I concluded that if we want decent sound effects in games, we must have samples, because you cannot create gunshots or explosions on a synthesizer. So samples are there, but they are at Amiga capabilities, meaning just 8-bit. And there is only 64 kilobytes of memory for these samples in the chip, so we won't be uploading any MP3s there. Now that asterisk I mentioned, samples can also be an input parameter for an FM synthesizer. So instead of rigid waveforms like sine or triangle, we can load a sample and use it as a waveform in the FM synthesizer. So we have a sort of budget wavetable prototype. In the picture, it consists of two components. We have a Raspberry Pico microcontroller, which contains the code for each individual channel, and it is executed in a loop 9 times for every channel, which generates our signal on the I2S output. This is inter-IC sound. Here we have a microcontroller, and that goes to an I2S codec, which converts this digital signal into an analog signal that we can then play through speakers. I managed to pack all these parameters into 64 registers for each channel, and they are organized in memory in such a way that we have a memory map of 64 registers, and the last register selects the channel for us. So if we enter 0 into the last register, the remaining 63 configure the 0 channel. We are 1, and those registers configure the first channel, and so on. The last register is specifically used to configure the chip itself. All right, we have some time today. Since I'm the last one, I can show you how it sounds on the speakers. Let's start with a demo playing on real hardware, that is, on this prototype. Since I do not have a dedicated music player written for this specific chip for the 6502 yet, I will play you a tune from SID that you all know well. I wrote a player that can convert music from SID to SGU-1, which also serves as a demonstration that the SGU-1 can play just like a SID. And here you can see that this is a dump of the SID registers that this player in Monty on the Run plays, and they are then appropriately converted into SGU registers.
However, you have to convert that music into notes.
Here is a Commodore player running, which writes to those registers in the memory area where the SID normally is. And after this player, an additional routine is running, which reads these pseudo registers and converts them into writes to the actual SGU registers. So here we have this module, this is the SGU, but here we also have the rest of my computer, which is invisible, and it controls it. And here is the screen dump. Okay, so this plays SIDs. All right, now a piece for 2 SIDs. Since the SGU has 9 channels, we can play up to 3 SIDs at once. And here is exactly the same method. So a Commodore player is running, and then twice that function converting from SID registers to SGU. If anyone wants, they are on the X65 project. That was the SID. Now let's listen to how the OPL plays. These are pieces written for OPL. This is for OPL2, and they are also played using SGU.
The method here is a bit different. What you see is Furnace Tracker. It is an open source tracker that...
Sorry, it is an open source chiptune tracker. It has a gazillion different chips connected as emulators. I simply connected the SGU-1 firmware to Furnace as a module. As you can see, the SGU-1 chip turned on right now, and I have loaded a chiptune composed for OPL2. I played it on my chip. Yeah, like OPL. Well, everyone here knows. I mean, yes, well, okay, not everyone knows, but if someone knows what OPL2 sounds like, then yes.
How those melodies come.
And that is exactly the point.
Exactly, that is the point. Yes, that is how it was supposed to sound.
But they were actually helpful because, like,
Maybe I'll fast forward this.
this musical genre.
The next one is a chiptune composed for the OPL, the original one that started this revolution. This one is mine too. That is exactly why the SGU-1 has 9 channels. So that OPL tracks can be played because other Yamaha synthesizers had 9 channels.
A track composed for OPM.
I did not speak about this very clearly before, but these features that the SGU-1 modules and operators have are modeled after the OPL, but they have expanded capabilities.
Because of that, tracks for the OPM also play. They play practically one-to-one, one parameter.
So the SID fans are happy, the OPL fans are happy, Kamilik is happy. I have one more demo. No, wait, I have one more demo. Just a moment.
Then it will be the full package.
The first chip that will play right now is the tilde arrow sound unit. So this is a fantasy chip built right into this furnace tracker. It is a chip that was a fantasy chip invented by the author of Furnace Tracker. He also had the idea to build himself a fantasy chip based on some of his own ideas. Well, it is quite similar to the SID. And the SGU-1 code is based on the tilde arrow sound unit. I took the tilde arrow sound unit code from Furnace Tracker and ported it to C because it was written in C++, and based on what the tilde arrow sound unit can do, I added that FM synthesis as an earlier module because the tilde arrow sound unit is very similar to the SID. So the whole SGU-1 is simply an extension of the tilde arrow sound unit. A community member suggested it when we were wondering what to do. Maybe use TSU. So I downloaded Furnace Tracker, played a few tracks composed for TSU. I decided this is it. And that was the first track I played. And now it will be played on the SGU.
And here, viewers, you can also hear it.
just doesn't look right here when very much, sort of.
It is a bit chip-tuned here because some tracks are played with samples, and the Arrow sound unit has samples.
I mean, some instruments.
Probably the drums as well.
Probably making it for yourself.
And there is the Amiga. Everyone knows how mods play. So we simply have here is currently a typical 4-channel mod written for the Amiga. Each channel is played by a sample, here by one. It plays the same samples I upload, I put into the Amiga, they fit without sound.
Why does the module also have a built-in effect that was included for those samples? Bipolar.
This is a sort of budget module, a delta module. I would have to spend too much time to convert the commands that are for Pola to the SGU. Because for Furnace Tracker, I just need to write a module that mimics the version of what plays on the SGU-1. And those Amiga effects were so complicated that I decided, let's move on. Is it playing? Let's move on.
Man, that was weak.
Well, don't put it down anymore. This caption is better.
Pokey.
Is it out of tune like Poke?
Not yet, maybe not quite yet, no.
This is quite a characteristic beat.
I mean, you can connect modules to Furnace Tracker here, but I just have ready-made modules. I am not a musician, unfortunately, and
I can't sing because I'm tone deaf, but I have a good enough ear that if I hear someone singing off key, then
And you didn't try playing that for me?
no, but it sounded more or less the same as OPL because those are synthesizers from the same line, only I played it as if on an OPL, just using one operator. And as I already mentioned to you that as part of developing this chip, I connected the SGU-1 code to Furnace Tracker. And that was a very cool development tool as well because it allowed me to tune the internal parameters of the synthesizer so that it would play like old OPLs, so that it would play just like the SIDE. So by running these modules in Furnace Tracker and tweaking the right parameters inside the synthesizer, I tuned it all so it would play as it should. It is not yet merged into the main Furnace code. The pull request is open.
Well, the tracker code is moving very slowly there. Maybe they will merge it someday. Anyway, if anyone wants to play around with it, the fork is available on the project's GitHub.
There are releases available to download for Linux, and I think for Windows.
It is for Linux. That is very good.
And now, SGU-1 is currently being built. It is being designed and built as a system on module. It will be available for purchase as such as a module. A postage stamp 3 by 3 inches. It is called a castaway module. The signals of this module are available on external pins. You will simply be able to buy this chip and solder it into your own design. And the test production run is currently going through PCBWay. I am waiting for them to solder it and send it to my home. I will be testing it. Yes, but the assumption is that it will simply be available for sale as a module. Buy a new synthesizer. A synthesizer, not exactly FM anymore, because not only...
But it will also be in the X65.
Yes, it will have the X65 soldered onto the exact same module instead of the SD1 that was there before.
But I have broader plans. I have already started drawing schematics for a Commodore 64 cartridge, actually.
No, please.
And I also plan to make a cartridge for Atari. SGU-1. SGU-1 also has inputs, not just outputs, but inputs as well. So in practice, you can just route the audio out from the Commodore and mix it through the SGU-1. Access to the mixer. You can internally mix these in channels in the SGU-1, but I also already mentioned that it will be available.
Stereo input and output.
Stereo input and output. We wanted things.
And of course, you can control the panning on every channel, left and right.
It is now time for questions.
Wow, what an amazing design.
Very much so. I am surprised that you presented yourself so well here, so to speak, the breadth of possibilities of these circuits, because it is actually very versatile and really brings out the best in everything, ignoring those few problems. I am basically also at the stage where that the sound is on the water, but overall,
Yes, but let me remind you again, my goal was not to faithfully recreate any arbitrary chip. It does not sound exactly like the SID. It does not sound it sounds exactly like the OPL, just cleaner, because this synthesizer has 16-bit synthesis internally, while the OPL only had 12-bit. Yeah.
I will ask one thing, and you must know this because you did it. And I am curious because I am not that involved. In this OPL, I say there are only operators. So for there to be sound, it is not assembled like those 4 oscillators.
Like when you do a Fourier transform, where you have a sound of any shape and you can decompose it into a number of sine waves, each with a certain amplitude. Well, here you have 4 such sine waves with certain harmonic frequencies, and you can set the amplitude for each. And if you layer them properly, you can even get a wave close to a square wave. It will be a bit jagged, but
Well, calling that OPL waveform a rectangle is a big stretch, because OPL is actually worse at those squares or rectangular waves, and generally the low end on OPL is very weak. And you have that FM cartridge, YM or whatever it's called. Generally, they adapted OPL for the Commodore 64. Only the Commodore had.
I even know why that is, because Yamaha's designers wanted this synthesizer to avoid so-called aliasing, which is that's an effect that appears when there is a sudden sharp change signal intensity, and then when you have a square wave, for example, you have a sudden change followed by some rippling. That is exactly what aliasing is, because harmonic frequencies appear that were not in the original sound, those extra ones. And when you compose sound exclusively from sine waves, that aliasing does not occur. Even if you layer some harmonics on top of each other, you won't have those sudden transitions. And in the SGU-1, I have a filter that cuts this aliasing. So even if you have a square wave, there is a simple digital filter that cuts this aliasing.
Wow, that turned out really well.
No, I am truly impressed. Aside from the fact that you are building your own computer, it is just incredible.
Yes, and that is the origin of the title of this entire presentation. It was only supposed to be a side quest, but it turned into a whole separate sub-project with its own soul, so to speak.
And a couple of sentences about this X65, a couple of sentences about the X65 itself. What kind of project is this? What is its goal?
X65 is a new modern 8-bit computer, designed from scratch as a new build based on integrated circuits that currently exist and can be bought in stores. And the premise is that so that I don't have to go dumpster diving for parts, and so that you who have this computer don't have to go around to retro shops and buy 8-bit port joysticks. You just plug in a USB keyboard, USB controllers, and play 8-bit games.
And what software will run on it?
It's original. This is not a design intended for emulation. It is a completely new computer with a new architecture. It is based on the Commodore 64 and Atari 8. Just as the SGU-1 is a mix of many different ideas, the X65 is a mix of many different 8-bit computers. Yeah, right. The graphics are similar to what was in the Commodore 64, Commodore TED. We have as many colors as in the Atari. I have a display list like the one in Atari 8-bit when it comes to graphics. The sprites are inspired by what was in the Amiga, because who takes an Amiga for sprites? Did I answer the question? One of the aspects is that we wanted this computer to also play like those computers from that era.
And that is where SGU-1 comes from.
And when is the premiere announced?
If you want to get your hands on the SGU-1, well, the station, the X65 station is downstairs. You can just walk up and play with this computer right now. At the moment, we are at the milestone 1 stage, which is the production of the development board. It is a small board for developers to play around with the hardware, but in the end, it will be a keyboard computer, a little Commodore.
This is just amazing.
For now, thank you. See you later.